So I sent you written solutions to the exam. I hope you received that. And by the final exam, you will also receive your midterm papers corrected. I will scan them and send each paper to the student to whom it belongs. Now today, we have, if I remember correctly, the last question on the midterm. We have not gone through that. Let's go quickly through that. Now here we have a metric space. A non-empty subset of the metric space. A is bounded with respect to M. Then we consider the set MXY, XY in A. So this is the set of all possible distances between any 2 points in cap X. Well, since A is bounded, this will have an upper bound. Since A is non-empty, this will be a non-empty subset of R. So by the supremum principle, the supremum of this will exist. And we refer to this as the diameter of A. That was the first part. The second part says if A and B, they're both non-empty subsets of X, both bounded with respect to M, this implies that A union B is bounded with respect to M. That was the statement which was to be proven in the second part of the question. Now, the idea here is, this is A. Well, this may or may not have an intersection with B. But what we can do is, we can fix a point in A and fix a point in B. Well, we can do that because they are both non-empty. So take any xy in A union B. Now, since A is bounded, there is, by definition of boundedness, some say M1 in R, such that for all xy in A, we have mxy is less than or equal to M1. But since B is bounded, there is some M2 such that for all xy in B, this quantity will be less than or equal to M2. And here, A in A, B in B fixed. So they have a particular distance, MAB, that will be larger than or equal to 0. Now, a bound for A union B, well, clearly then will be M1 plus M2 plus this distance. So set L equal to M1 plus M2 plus MAB. Now, when you take any xy in A union B, well, if xy, they both belong to A, then mxy that will be less than or equal to M1, but that's less than or equal to L, because M2 and MAB, they're both non-negative. If they are both in B, then MXY, that will be less than or equal to M2, that will be less than or equal to L. When X is in A and Y is in B, then this will imply that MXY, that will be less than or equal to MXA. X is in here, so we take its distance from A. Y is in here, we take its distance from B, plus MAB plus MBY. But now this is less than or equal to M1, this is less than or equal to M2, so this is less than or equal to L. Well, if X is in B, Y is in A, well, you proceed similarly. So this shows that A union B is bounded. Finally, in part C, you again have AB in X, both bounded, and A intersection B. Well, the typo was that this was empty, but if this is empty, the claim, of course, is not true. The claim is that diameter of A union B is less than or equal to diameter of A plus diameter of B. Now, although that this is a typo, it's rather clear. The rule is, if you show that under the given circumstances, the given claim is not true, according to the superiority of law, you get full points. If you correct this and do it, well, then you get again full points. Well, otherwise, well, it has to be assessed according to what's in there. So, okay, but this is now, well, and here, A intersection B, that's non-empty, so you can take some W in the intersection. Now here, if you show that diameter A plus diameter B is an upper bound of the set, that completes the proof. Refer to this set S, because diameter A union B is the supremum of this set. Well, if any number is another upper bound of that set, then the supremum, being the least upper bound, will be less than or equal to that. Okay, then let us show that diameter A plus diameter B is an upper bound of this set. Now for that, we take any xy in A union B. Then mxy, that will be an arbitrary member of S, but then that will be less than or equal to, well, now let me write it like this. xw plus m wy. Well, let me again consider here, instead of doing it like this. Now, if xy is in A, then this is less than diameter A. If xy, they're both in B. This is less than diameter B. If one of them is in A and the other is in B, then this will be less than or equal to m xw, they're both in A, plus mwb, they're both in B. So this will be less than or equal to diameter A, because diameter A, that's the supremum of the set of all mxw's when x and w are in cap A. Well, the supremum is, in particular, an upper bound, and this will be less than or equal to diameter B. Well, if x is in B and y is in A, then this follows similarly. Thus, in all cases, diameter, and this is less than or equal to diameter A plus diameter B, and likewise in here. So diameter A plus diameter B is an upper bound of S, where S is this. So supremum of S, that's less than or equal to the sum of these. And this supremum is just the diameter of A union B. And that completes. This is actually what we did when we considered the proof of, in a complete metric space, total boundedness and closeness that's equivalent to compactness. Okay, because we took two within a non-disjoint, that is intersecting, non-emptily intersecting sets in the sequence, and we use this, and that's okay. So you have written solutions as well. Any questions concerning the exam? Okay. Now let's then pass to the second part. The second part will consist of two parts again. Well, in one I will talk. In the second part you will talk, and you will assess what we have done, your criticisms, your suggestions, and so on. But this will consist of two parts. Now I will go over what we have done in rough lines. Well, that's what we did at the beginning as well, but now it might be more meaningful. Now, where we considered R, which was the main building block of the n-dimensional space, Rn, we took its algebraic and order structures as given to us. Well, we said that does not suffice to characterize R within its entire structure. We need one more structure. And that was the so-called topological structure. Thus, we assumed the supremum principle. We claimed that what we know and what we take as granted to us concerning the algebraic and order structures, if that's combined with the supremum principle, that will give us the entire information about R. Well, we have not gone through that explicitly in the context of R, but I guess we had enough instances to show the importance, to see the importance, not to show, to see, to observe the importance of this supremum principle. Okay? And the first simple observation was, if you have some non-empty subset of R, and Y an upper bound of S, Y turned out to be the supremum of S if and only if Y was arbitrarily close to S. That was our first observation. Secondly, we considered a real-valued function defined on a finite set, then its maximum and minimum both existed. Well, we said, fine, but that's too restrictive. Can we consider a broader class of domains such that when we actually put also some conditions upon the function so that it's well behaved, can we guarantee the maximum and minimum of a smooth function on a domain with that property, real valued, to possess both its minimum and maximum? Well, we got compactness for the domain and continuity for the function itself. But continuity was close points in the domain being mapped onto close points in the range. Well, but as we bring the points into domain arbitrarily close to each other, that means the images, they should get arbitrarily close to each other as well. So, well, that was the second instance where the notion of arbitrary closeness played an explicit role. Okay, so, well, then we said a topological structure actually is one which allows you to precisely decide, given a point and a set, when is that point arbitrarily close to that set. Well, then we defined a topological structure in terms of open sets, but we also have noted, well, if you actually give an entire list of pairs consisting of a point and a set, such that, well, they specify the point being arbitrarily close to the set, together with some consistency conditions, you can define the topological structure by that as well. So, why? That's an upper bound of S if it's arbitrarily close to S. In that case, it becomes the supremum. But the supremum, that becomes the maximum when that point belongs to the set. Okay? Well, you can say we discovered this in terms of a metric, and, well, if we confine ourselves to Rn, well, we can do with metric, well, what's the use of topology, that more general construct, what's its function within this course? Now, it has two functions. One is, if you need to internalize, make your own, a particular mathematical or non-mathematical structure, it's always better to go a bit beyond that, to embed that into a larger structure. Because in that case, you will also know what the particularities, what the specialties of that structure, what you need, is within the larger picture. That's one. But secondly, we will use that in the second semester as well as in economic theory elsewhere. Why is that? The main reason, one of the main reasons why that will turn out to be useful in general is the following. Well, in economics, be it macro or micro, makes no difference. If you consider best responses of the agents involved, it might be to given prices, it might be to a particular policy that the public follows, it might be within the context of a game, a joint action of the others. The best responses usually are not unique. So best response functions are usually set-valued. But in that case, if the variable to which you have a response changes a bit, what does it mean? That the best response sets change a bit as well. Thus, you need a notion which tells you when is a set arbitrarily close to a collection of sets. And in that, you cannot confine yourselves to a metric. You need the topological structure. So for all equilibrium existence theorems in economic theory, now, as I said, be it in micro or in macro, you need a topological structure. You cannot do it just with metrics. Okay, so that's it. Well, in our end, the notion of compactness that boiled down to being closed and bounded. But we have seen boundedness is not a topological invariant. It depends upon the metric. And we wish to have some simple counterpart of Heine-Borel theorem within the metric spaces. Then we just tried, well, whether the notion of total boundedness will do. We then first check the total boundedness and boundedness in a Euclidean space, they coincided. So that was good news. Well, in general, in a metric space, compactness implied total boundedness and closeness. But the converse was not true. And the reason, well, we observed in the example which exhibited that the converse was not true, well, there were gaps in the space. Well, it was the set of all irrationals. And, well, no matter what the set of rationals or irrationals makes no difference. And whatever two rational points you take, well, there are irrationals in between. Well, then we reached the notion of a complete space, and in a complete space it turned out that total boundedness and closeness was equivalent to compactness. Okay? And here we also, by the preservation of compactness under continuous functions, that allowed us to show if you have a real valued continuous function on a compact set, then it attained both its maximum and minimum on that set. Okay? But then this was all about existence, how to find the maxima, minima, and the points at which those maxima and minima are attained. Well, then we considered differentiation. Well, we introduced the notion of the derivative as a linear map. We extended to Rn. And, well, we have seen that it is the directional derivative, actually, which played the major role in deciding whether a point corresponded was a maximizer, a minimizer, and it was a simple observation. If it's maximizer, If you move away from that, you have to go downward if it's a minimizer. If you move away from that and stay still within the domain, and that yielded. But that was again one-sided. If you had an interior point and the function attained a maximum or a minimum at that interior point, then the derivative as a function should be the zero function. But the converse was not true. Then we asked, can we now actually restrict the functions we consider to a smaller subclass where the converse is also true? Well, that led for maxima of the notion to the notion of a concave function, and for the minima to the notion of a convex function. Now then we considered all properties of concave and convex functions within the context of R and extended them to the general n-dimensional case. Now we had two important results. If the function is strictly quasi-concave, then it can have at most one maximizer, one point at which the maximum is attained. And well, strictly quasi, this is actually the precise reason why one introduced the notion of quasi-concavity and quasi-convexity. That's the function of. And we also had a partial converse to the derivative of being zero. Well, if you have a maximum or a minimum at some point, then the derivative of zero is zero. But if the function is concave, and if the directional derivatives exist in the direction of all vectors which point into the set at the point, well, then we got also the converse of that, okay? But now, what awaits us is maximization and minimization under constraints. Because in economic theory, well, almost all optimization problems are constrained. So, well, next we'll consider Lagrange's theorem, which is the most classical theorem of optimization under constraints. We will also see that it's quite related to the way we have defined the derivative. That will be useful in there. But then we'll extend that to the concave programming theorem, and we'll end up with Kuhn-Tucker theorem as the most general tool. But for that, we will need separation theorems. Separation is very closely related to optimization. And well, so for separation theorems, we need separating objects. Well, a point is separating in a line is separating in a plane is separating in R3. Well, then we introduce the notion of an affine subspace of Rn to generalize points, lines, planes, and then the notion of a hyperplane, which is a separating object in Rn, a hyperplane in Rn. So we are now at the brink of introducing separation results. So that is what we have done. We have done not much. Okay, so well, it took just 10 minutes to summarize everything, to go over all theorems. But we have done something else. We did not consider, and well, one more yardstick. When we reach Kuhn-Tucker theorem, you can go back. You can go back to the first hour of this course, 515, and you will see that we took the shortest path, which takes us from taking granted the algebraic and order structures of R to reach Kuhn-Tucker. So you cannot actually take any part away from that chain, then that chain will get broken. Okay, but we did something else. We actually attached importance to being precise. We did not just consider the theorems as tools. Well, you can forget about the proof of a theorem and use that as a tool. How is that? Well, you know what the hypotheses are. You can apply the theorem, well, in contexts, in environments where the hypotheses are satisfied. But that actually reduces mathematics just to a language, just to a useful tool in doing things in other areas. Well, it is not only that mathematics does not just consist of that. The most useful part of a mathematical approach to other areas is the expression, the precise expression of causality relations. Now, in any science, well, how can you describe science to someone in the street? Well, you can say, well, it's a systemic and general knowledge about objective reality. But if you just observe a particular phenomenon, describe all the possible properties pertaining to that, now that will be confined to that particular phenomenon only. It will not be something general. How can you reach general information about objective reality, which can again be tested against reality and can pass that test? It is only if you go beyond the appearances of singular phenomena and if you can discover the causality relations behind them. What implies what? That discovery, the place that that discovery is made in science, that's theory. What you do in theory is you actually reconstruct the main relationships, the network of relationships pertaining to objective reality via appropriate concepts. You make a model, a mental model of objective reality, where you can actually deal with implications, causality relations. You can express statements which reflect causality and which can be tested against reality. Without theory, you cannot do that. Well, that's true in economic theory as well as it is true in all natural sciences and other sciences. But it is mathematics which deals with causality relations. So the very approach of mathematics, well, that is very useful in constructing models, not just quantifiable. Well, if things are quantifiable, then we can use mathematical tools. That's correct. The main notions of mathematics are numbers. But there are areas of mathematics where you use numbers just in numbering the pages. So mathematics is something far beyond that. And here in this course, we also tried just to give a small flavor, a taste of what that is. Okay? Well, I also said in the introduction, well, Einstein says that nature is mathematical. So that's why we can use mathematical methods, mathematical notions, mathematical concepts in describing nature. I think it's just the other way around. Mathematics itself is natural. The rules of logic, they are not a product, a sheer product of human mind. We derive them from relationships which pertain to objective reality. Well, you see, when it rains, there are always clouds. But it might be cloudy and may not rain. Well, that means clouds are necessary for rain, but not sufficient. If it rains in the absence of clouds, that would be something which has not been observed so far. Okay? So you can actually multiply those examples. So we also try to give the mathematical approach itself, and we'll continue doing that in the next semester as well, so that it is useful for theoretizing, for the formation of useful conjectures which can be tested in economic theory as well. One more remark and then the floor will be yours. Economics actually consists of two parts. One is positive theory and the other is design. In positive theory, you try to discover what governs the development outside you, which exists, what already exists, without any human interference. The building blocks are humans, but they are in certain relationships, but that's come into being in a spontaneous way. It was not the product of a design. So positive economics deals with discoveries, facts concerning what already exists. But design, on the other hand, goes the other way around. You have some social economic objective, then you ask the following: given the particulars of the existing society, can we design an institution, a mechanism, a regulatory rule, norms, which actually will take that society and enable it to reach the aim, the target you had in mind? Well, in that case, the institutions, the mechanisms, the rules you're dealing with are not discoveries anymore, but they will be inventions. Especially in this part of economics, which I think will play more and more a more weighted role, because what we do know, positive economics, that will get exhausted, and it's exhausted in many different areas. In general equilibrium theories, there's not much left to be done, for example. But design will become more and more important, and in the design part, mathematics actually plays a more important role than in positive economics. So that also is a particular relationship between mathematics and economic theory. As the last item for this design part, well, sometimes, when the entrance examination, the university entrance examination comes close and students are around to learn about the universities, about the topics, well, when they ask me, well, what is economics? Well, I usually answer the following way. Well, I'm not an economist. I'm an outsider, so you can ask this to economists, but what I know about economics is the following. Economics is the only branch of science which will annihilate itself when it becomes successful. When it becomes successful, there will be no need. When everything, you have an abundance of everything, when there is no shortage, if that's the aim of economics, to get rid of shortages, so that everyone will become happy and no further happiness via economic tools will become impossible. Any improvement in happiness just via economic tools, well, then there will be no need for economics, but there will still be a need for mathematics. Okay. So, well, I left you very little time, but the floor is yours.